And welcome to Climate Chat. I'm your host, Dan Miller. And today our special guest is Bill Diamond, the CEO and president of the SETI Institute. And I think a lot of you out there know who SETI is, but we're going to find out for those who don't in just a moment. Just for upcoming program notes, next week, next Sunday, we have Brett Henkel, the co-founder of Svante, a carbon capture company. We're going to talk about carbon capture from pulp and paper mills, which avoids almost all the criticisms that people have about carbon capture. So that should be an interesting show. And also, just as another programming note, we just had an interview with Bill McKibben, and some of you might have missed it because it was on Wednesday, not our regular Sunday time. So if you missed the interview with Bill McKibben, please check that out on the Climate Chat homepage on YouTube. Very good. So Bill, welcome. We have a lot of Bills. Bill, welcome. And it's great to have you here. First, let me just give you a brief background on Bill. So Bill Diamond is a Silicon Valley technology veteran and current president and CEO of the SETI Institute in Mountain View, California. The SETI Institute is a nonprofit astrophysics and astrobiology research and education organization focused on the study of life in the universe. Prior to joining the Institute, Bill held various executive management positions in applied technologies. So it's great to have you here. And you want to expand on that, the bio at all? Like what brought you to SETI?
Well, that's a good question. My background is physics, and of course, when you study physics, one of the things you study is astrophysics and astronomy. So I would say that even from a fairly young age, I was a wannabe astronomer or an astrophysicist, but probably thought myself intellectually incapable of achieving that objective. But I've always been fascinated by space science, by exploration, by the cosmos. Grew up with Cosmos and Carl Sagan on television, who was an inspiration to many in our field. I went into applied technologies, and lasers and photonics, fiber optics is where I spent most of my career. Actually, I guess I would say involved in developing the technologies that fundamentally, support the internet, basically, and make all of this possible. But in any case, I grew up reading science fiction and really, again, enjoying the kind of mind-expanding elements of astronomy and astrophysics. So a good friend and colleague from Bell Laboratories of mine managed to get on the board of directors of the SETI Institute years ago. And I wondered how he was able to do that, but I was very jealous. But lo and behold, at one point after a business I was in photonics was sold to another company, and taking some time between, he reached out and said, "Hey, we have some issues at the SETI Institute. I'm on the board there. Could you come and help us?" I said, "I'll be there in 10 seconds or less." And I arrived, and this was back in 2015, and helped them out for a few months, and that morphed into would you consider staying and overseeing the institution. And I said again pretty quickly, absolutely. So that was 10 plus years ago, and haven't looked back. It's been the most interesting and fascinating part of my career, and I've had a fun and enjoyable career over many, many years, and had the privilege of working with a lot of amazing people. But this has been something next level, I guess.
Very good. So now I've known SETI since, I guess, a long time ago, founding, because I was on the board of the Chabot Space and Science Center for 20 years, and relationships there and whatever. So I've known a lot about it. And my guess is that a lot of people listening do know a lot about SETI, but there will be a few that don't know about SETI. So before we delve into SETI and climate change on Earth, can you just give us a little background on what is the SETI Institute and what does it do?
Sure. Well, the SETI Institute is a name based on an acronym and an endeavor. The acronym stands for the Search for Extraterrestrial Intelligence. And so SETI is both an endeavor as well as an institution. And traditionally, SETI, which dates back to about 1960 when the first SETI experiments were done, is based on the idea that other advanced technological civilizations elsewhere in our galaxy or potentially beyond would be undertaking activities as we have done around about for 100 years now, where the phenomena that they're using, things like radio and radar and so forth, would be detectable over vast distances with radio telescopes. So traditional SETI has been searching for signs of technology as a proxy for life and intelligence elsewhere in the universe using primarily radio telescopes. It has expanded since then to more broadly look for technosignatures, which would include anything, including, for example, chemical constituents in exoplanet atmospheres that might suggest the presence of industry or technology on the surface. In other words, chemical compounds that nature doesn't produce. And there are a wide range of other so-called technosignatures. But the Institute, almost since its beginning 41 years ago now, has also been doing a broader study or inquiry in a field that is now called astrobiology, which basically means the search for or the study of life in the universe. And in that context, we do everything from astronomy and astrophysics to climate and biogeoscience to exoplanet research, planetary exploration, astrobiology, and the study of life in extreme environments, and SETI. So we have a wide range of research conducted at the Institute, over 100 PhD scientists representing 22 distinct backgrounds in the natural sciences who come together to really unite around the one science question that drives the Institute, and that is, are we alone in the universe? But astrobiology also includes, looking for things like microbes on Mars. So whether it's microbes or intelligent technological aliens and everything in between, our institute is devoted to the study of the possibility and likelihood, in fact, of these of life beyond Earth, and how to look for it, how to characterize it, how to evaluate it, and of course that also includes what are the conditions under which life emerges and is sustained and evolves, which gets us, back to things like climate change.
Okay. Well, speaking of that, so the timing of your interview is really pretty good, because we had Jim Hansen, one of the best known climate scientists, on 2 weeks ago or so. And then he hinted that he's working on this other thing. And then he published on it the following week. And we did a show on that last week, which was how we can look at the planets like Mars and Venus and understand better the dangers we're facing on Earth about climate change.
Absolutely.
So that's kind of a little microcosm of what we're talking about today. But so given all of that, what are some of the research areas of SETI that are informing us about climate change here on Earth?
Yes, I would say that probably the most direct, and I should say, our activities and endeavors are not specifically geared towards climate change. That's not the nature of the research we do. However, it is directly involved in the research we do because of what we observe. So in terms of the methodologies and modes of research that we do at the Institute, we use ground and space-based optical telescopes. We use ground-based radio telescopes. We do laboratory research. We do theoretical work. We do advanced data analytics. We do technology development. But we also do field expeditions, which means we have scientists who work all over the world in some of the most remote places on Earth, including one of our scientists who scuba dives under 4 meters of ice in the Antarctic and studies colonies of cyanobacteria in that extreme environment. And so as a result of our scientists being in some of the coldest, hottest, highest, and lowest places on Earth, we observe over time the consequences of climate change. We see what happens to ecosystems, to the reductions in biodiversity, things of that nature. So it's the direct observation over time of what we see when we are in the field in various places that I would say is probably the most direct link to climate change, specifically on Earth. But to your point made just a moment ago about looking at environments on Mars and Venus, one of the reasons we do research in the field is some locations we go to are what we call analog sites. So the top of a volcano at 20,000 feet in the Andes is a lot like early Mars a few billion years ago. So we'll go to these environments to study what is going on in these environments and how they can inform us about doing things like looking for life elsewhere, and about what are the conditions for habitability. and for evolution and for sustained development of species from microbes to complex organisms, ultimately to intelligent and technological beings. So all of it connects through that lens. But the extreme polar regions of the Earth, for example, are anywhere from 4 to 10 times more sensitive as an ecosystem to the effects of climate change than we are in the middle latitudes. So these are wonderful places. Wonderful maybe isn't the right word, but very informative places to observe and evaluate what is happening with respect to climate change, because the impact is more readily observed and is happening more quickly.
Now, when it comes to SETI, one of the most famous, I understand one of the most famous equations in the world, maybe only second to E equals mc squared, is the Drake equation, even though people might not know what the actual Drake equation is. It looks very long, but just popped it up here on the screen. And what the Drake equation says is it's trying to calculate how many alien signals we should be detecting when looking out into the night sky. And so just to sum it up, basically, N is the number of let's see, the number of intelligent alien species we detect, right?
No, close, yes, but intelligence doesn't necessarily mean detectability. We've had intelligent species on Earth, including the human species, for hundreds of thousands or millions of years that have not emitted signals that could be detected. So N is estimated to be the number of technological civilizations beyond Earth that we would have the possibility of detecting based on their activity. And to run through it quickly, if you'd like, when you do that, the next variable, R sub star, is the birth rate of stars. It's the life cycle of stars. And this entire formulation, where N is only meant to be an estimate, it's not meant to be, this is not intended to derive a precise answer to the question. But it was an effort to answer the question, how many technological civilizations might there be in our galaxy? And that question was kind of the background question to that is, does SETI as an endeavor make sense? And this was a question being asked by the National Academy. So Frank Drake, Carl Sagan, and Otto Struve, and several others met at the Green Bank Observatory in 1961. Frank's job was to come up with an agenda. And so he started writing down the questions that he felt needed to be answered if we were going to estimate, the number of technological civilizations there might be out there. So he thought what is the birth rate and life cycle of a star, and how many stars or what fraction of stars have planets? That's F sub P. And if there are planets, what percentage of those, or what number of those planets might be Earth-like habitable planets, in which the mass of the planet is not too big, not too small, and the orbit of the planet around its host star is just right, where theoretically liquid water could be maintained as we believe, a pretty key ingredient for the development of life. And if there are habitable environments, in how many cases might life actually emerge? That's the next variable, F sub L. And if life emerges, in how many cases might intelligence arise? And that's F sub I. And if intelligence arises, in how many cases might F sub C, or rather, in how many cases might technology arise? And that's F sub C, C standing for communication, where the technological activity of the civilization could be detected by those of us here. And then lastly, and I think most provocatively and most relevant to this conversation, the L variable, which is how long does a technological civilization remain detectable? And so this formulation, I mean, it looks complicated. It's not. It's just like, a product, and you go through a funnel. The further to the right you move, it's a little bit like, I often explain it as, how many kids play Little League baseball, and then how many go on to play in high school and college, and how many make it to the major leagues and so forth, and then how long is their career. So you can think of it that way. But from our point of view, it's a good analogy. From our point of view, it's a roadmap for astrobiology. That's the way we see the Drake equation. And so most of our scientists, for example, would say that they can associate themselves with one or more of the variables of the Drake equation, because that's the area that they work in. But this is, very fundamental. It's an interesting way of looking at and addressing this question. And of course, things like climate change fit extremely well into this construct.
Yeah. So before we get to the L, because the L is a critical one here for us as well. The rest, I think, we learned a lot about how many stars. We're getting a good feel for that, how many stars are, and we're also getting finally a good feel for how many planets orbit stars, and then the habitability factors. So when you just look at that and put the L aside for a moment, I think the general numbers would be that there should be many uh, uh, technologically advanced civilizations we should be able to detect, even if you only assume, well, 1 out of 1 million planets that are habitable could have life habit. You pick any kind of numbers you want. There are just so many stars in the galaxy. There are so many, planets that you pick any number you want. There still should be many, yet we don't see them. Is that did I characterize that correctly? So
yes, I think you did. I would say that the statistical probability that we're alone in the universe is zero. But the most abundant neighbors are likely to be microscopic or microbial life. So as you go further to the right and advance beyond microbial life or basic life into complex organisms, intelligent species, and then ultimately technological species, the number is going to get smaller. And the distances are vast. They're very difficult for people to wrap their heads around. I mean, our closest neighbor star is Alpha Centauri. It's 4.2 light years away in a Milky Way galaxy that's 100,000 light years across, which is one of hundreds of billions of other galaxies. The fastest spaceship we've ever built is New Horizons, at least going in a straight direction. And that's the one that flew past Pluto back in 2015. You may recall that NASA mission. That's the fastest thing that humans have ever created in terms of moving along a vector. And if you sent that to Alpha Centauri, our closest neighbor, it would take 80,000 years to get there. And so the scale of things is difficult to imagine. Also, a civilization, and this ties back to the L variable, that becomes technological. How long is the window of their detectability? If they don't last very long, what is the probability that two technological civilizations might locate one another in the vastness of the cosmos? So it's kind of a really interesting phenomena when you start getting into questions of time and scale, which I think also tie back to climate change, because one of the problems with climate change is the time scale over which it is functioning. But from our point of view, I mean, I think, and maybe Dan, you can help me get this quote famous or to be known for this quote. But something I said actually even before joining the SETI Institute was, I think the most remarkable thing we may discover about life is that it's not remarkable at all. And not to say it isn't amazing, but that it's going to be all over the place, as you said. I mean, the building blocks of life are the most basic and most abundant elements in the periodic table, and they're everywhere in space. And so, it stands to reason that it's happened before. But you mentioned planets, exoplanets, and it's amazing. But the factual evidence, the factual knowledge that planets outside of our solar system even exist only goes back to the mid 90s.
Yeah, no, very recent.
Very recent.
I mean, well, we thought they were there, but in terms of actually detecting,
a lot of people thought they were there. Some weren't so sure, but they were discovered in the 90s. Some large Jupiter-sized planets, which were easier to find. And the NASA's Kepler mission, which actually was born right at NASA Ames down the street from us in Mountain View, taught us that planets statistically are ubiquitous. That every star in the sky is effectively a solar system, and that planets likely outnumber the stars. And it was also able to estimate that approximately 20 to 30 and perhaps more percent of these planets are habitable environments. In other words, are Earth-like habitable zone planets in the right orbital distance. So that suggests in our own galaxy tens of billions of potentially habitable worlds among hundreds of billions of other galaxies. So again, the numbers are extraordinarily large. It doesn't mean the task is easy, but the statistics are pretty overwhelming. And that's new knowledge. The Kepler knowledge
Right.
really was in the 20 teens. So it's really that's been game changing. So now in the Drake equation, we pretty much have numbers that we can fill in out to and including n sub e, and then f sub l and I and c and l. These are the domains of our research. I call them
Mhm.
job security. So
Yeah. So now we get to L. And so there's something called the Fermi paradox, which is essentially the same thing, saying, hey, the numbers say there should be lots and we don't see them. Why is that? And it could be that L, or the amount of time that an advanced civilization is around to transmit radio signals that we could detect, is very short. And the reason could be that once you get to that place, you destroy your civilization by not taking care of the environment and things like that. And the proof we have of this is right here on Earth,
yeah,
where we are now transmitting for, let's see, 1920s, maybe. Yeah, so
about
about
100
100
years.
years,
Yes.
roughly 100 years, we're transmitting radio signals out into space, not on purpose for communicating, but just to have radio programs and TV programs and things like that. And now, of course, more recently on purpose using radio telescopes, whatever. But that's only been 100 years, very short amount of time in the overall
Right.
scheme of things. And yet, as we're covering on this program all the time, even though we're supposedly very smart and we can set up organizations like SETI and we can have astrobiologists looking at this, that, and the other thing, as I once put it, or I don't know if I was the first, I'm sure I'm not the first one to put it this way, but like as individuals, we can be very intelligent, but the more people you put together, it's more you get to be like algae in terms of the intelligence of everything. Like we're all in a petri dish and we're eating our way out to the edge. And somebody looks up and says, wait, is that the edge? And there's a shut up and keep eating, like, so
Yeah.
seems to be what we're doing. We're not acting intelligently at all because we know about climate change, we know about overshoot, we know about environmental destruction,
Right.
and we know these things, and yet governments don't act on these things to any enough. Let's just leave it at
Yeah.
that. So for our own civilization, we're threatened with extinction within literally hundreds of years of first transmitting the radio signal.
Yes.
And so maybe the Earth is telling us more about SETI than SETI is telling us about Earth. I'm not sure, but
Well, probably, and hopefully there's, bidirectional knowledge transfer here. But yes, I mean, this is a very significant possibility. This is something I've spoken about many times, is that, one of the possible answers to the Fermi paradox is the L variable, is how long does the technological civilization remain detectable? Now, there's lots of other issues here. I mean, the search for life is using very specific tools, and we're looking for very specific phenomena, but there may be lots of different phenomena and different ways to look. And civilizations, 1,000 years more advanced than we are, should they exist, may not be using any technologies of the sort we can detect at all. So and then there are other questions like, should we assume the motivations of other intelligent and technological species would be the same as ours, and that they would be transmitting or emitting things. And so there are lots of different perspectives for looking at the Fermi paradox, which I love as well, because it's not even a paradox. It's just a question. It's a good question, but it's not a paradox.
Right.
But in any case, it's I think that the L variable issue is important. So one of the things that is clear, and it has been clear since we started developing both tools and industry, and then ultimately technology, that in the case of technology in particular, and I include here things like the internal combustion engine, that there are unintended consequences associated with the development of new technologies that we don't think about at the time. In fact, one of the more interesting unintended consequences that we are thinking about in parallel with the development of the technology is AI. And people, right from the get-go, are wondering about, what are the unintended consequences and the potential dangers of using AI. But we have not done that with other technologies, really. Although, it's pretty well documented that engineers and scientists within the oil and gas industry wrote about and acknowledged the potential threat of long-term use of fossil fuels.
That's true.
And that
And then
knowledge
they
was
did it.
suppressed by the companies. So we have looked at this, but if one of the associations or one of the consequences of becoming technological is the unintended consequences of that technology. It could be that the onset of technology is also the onset of the self-destruct button, and that civilizations, it's a filter, and civilizations don't make it past, that point. At the same time, I've used the same argument to say that if civilizations have gone past their technological adolescence, let's say that that's where we are, and survived, and they've solved the kind of problems of their own making, they've had to do that through global cooperation, through coming together as a single species on a single planet and acting as a whole instead of as independent nation states with independent motivations. And they've had to solve really intractable problems. And if they've done that, they're probably not malevolent, which addresses some of the concerns that some people have, like all advanced species are, just going to kill each other. And I'm not sure I buy into that. But in any case,
although they're much more intelligent than us. Now, if someone says, like, one of the concerns of AI is they're going to be way more intelligent than us.
Yeah.
And it said, well, if you want to know what that feels like, ask a chicken. So, chicken is reasonably intelligent. I mean, compared to a microbe, but not compared to humans. And the more intelligent species seems to dominate everything else, right?
Sure. Well, domination is one thing, extermination is another. So, I mean, we don't purposely, as a species, intentionally exterminate every other species on this planet, plant or animal.
But we are in the process of doing exactly that.
Well, we are,
but not intentionally.
Exactly. It's not by design, and that's a key difference. But I think one of the problems, and this gets back to this question of why aren't nations and organized parts of society and civilization addressing the problem. And I think one of the issues is the time scale, that the time scale is such that, we act when we see a catastrophe, unfolding or close by potentially. I mean, we have this vast insurance system that studies risk and makes, that has actuary tables in, well, what's the likelihood of a fire or this or that? We should be looking at the climate crisis through that same kind of lens. What is the risk? Instead, we're looking at it from the point of view of, what is the science behind it? And, can we rely on the science? And there's a great book out there called 5 Times Faster, written by an English economist and policymaker who's devoted most of his professional career now to climate change. Where he makes the point that, science is in some respects the wrong lens through which to look at the climate change problem, because scientists are trained to be extraordinarily cautious about making, bold statements, especially based on sparse evidence, and doing things like projecting and forecasting. That's better left to maybe, engineers or risk assessment folks and so on. But, if we look at a problem, which, yes, that's a problem, but the economics and or challenges associated with addressing that problem now are hard to justify, to our society and, our tax base and so forth, because they don't see them or feel them or realize them. And, this is the proverbial kicking the can down the road.
Sure.
So the problem is not at our doorstep, although I think it's much closer than most people think, and it's moving faster than most people think, including scientists. I'll go out and make that statement as well. I think it's happening much faster than people imagine, and it's only going to continue to accelerate, and it's going to create problems on this planet, the likes of which we've never seen, in terms of even things like human migration. You think we have an immigration problem now, wait until, we've got another few degrees of global warming. So, but, I think there's also this notion on the part of some that might suggest that climate change is somehow anti-business or anti-commerce or anti-profits, and that's such nonsense. It is certainly anti certain industries that are accelerating the problem. That's true, but that doesn't make it anti-business. Anything but. In fact, what I say to people is, look, addressing the climate change problem and the kinds of engineering and technologies and solutions we're going to have to derive to deal with this and mitigate this is probably the single biggest business opportunity in the history of humankind. So it's not anti-business. It's quite the contrary. But we need to get to work, and this is something we're not doing.
Yeah, but speaking of what you were talking about, I mean, one of the quotes I say, that I didn't come up with it, but is that climate scientists are conservative in the opposite way that a risk manager is conservative. And speaking of risk manager, we did a whole show on the University of Exeter's faculty of actuaries. These are the people that do the calculations for the insurance companies.
Yeah.
And they took a look at climate change and said the whole way we're looking at it is so far off from the way we should be looking at it.
Exactly.
And I'd also I challenge you a little bit. You said that we don't know about it. Actually, well, as you mentioned, the fossil fuel companies use the word catastrophe when looking at future climate change from burning fossil fuels in the 70s. We've known about this, the whole world's known about this since the 50s to the 80s, depending on when you want to pick the start time for when our knowledge was. And we certainly know everything we need to know now. And yet we still find it almost impossible to act seriously on it.
Yeah, well, exactly. And I think, we is an interesting term here, because we, the human race and certain people within our society, writers, scholars, educators, people like you, me, others, we know about it. But, to what extent does John Q. Public know about it, feel it, experience it, worry about it? It's not so clear. I mean, anybody living in Northern California or Southern California, or now, thanks to climate change, almost all parts of the world, is very much aware of the risk of fires, wildfires. That could happen here right outside my window, tomorrow or a week from now or a year from now. So that's a visceral, it's a real risk. And I think, most people are aware of that, but most people may not necessarily link it back to climate change. And I don't think that most people really do have the sense of urgency that some of us do around this issue, which I think is part of what prevents us from taking the kind of steps that we should be taking.
But it's not that we can't know. It's just that the systems within the society, the media, certainly the political leaders, they don't want John Q. Public, I guess, to be talking or worrying about it. So they don't bring it up, right? And so it's not that we don't know, or yes, I mean, the public is not aware, but it's not because of the lack of knowledge. It's because this is a purposeful thing
the knowledge is
here,
there,
where society or whatever you want to call it, the we part, somehow the operational part of it is preventing action. And by the way, speaking of AI, it's the people developing AI, the leaders of doing that, who have said this is potentially an existential threat to civilization.
Yes.
They're the ones saying it.
Exactly.
And then they say, and they not 100%, but they say like 20% chance it'll destroy humanity. Okay, that sounds pretty serious to me. And then they say, but we're going to do it anyway, because if we don't, someone else will. They come up with some excuse. And so we seem to not have the ability, even though we're, quote, intelligent, to act on danger. And I think one of the reasons, speaking of an astrobiology point of view, I always say it's because we sort of grew up on the savannah a couple 100,000 years ago, when the only two important things were what am I going to eat today and what's going to try to eat me today. And something 2 weeks out was like irrelevant to your survival.
Sure.
And now we're talking about things that are 10 years out, 30 years out, 100 years out. And it means absolutely nothing to us, it seems, in terms of acting.
Well, that's true. And this is why, I think in part, again, astrobiology and even astronomy and astrophysics, I mean, they lend themselves a bit to this conversation because, we do think on timescales that most people don't think about. And, 10 years, 50 years, 100 years is a microsecond, on a cosmological time scale. So this train is moving very, very fast. And but But you made the point, and I totally agree with you. The knowledge is there, but the dissemination of that knowledge is A, not very effective, and B, not very widespread. One of the things that I get concerned about is much of the conversation happens around the notion of global average temperature rise. And, an average global temperature increase of 1.5 degrees or 2 degrees, and how catastrophic that might be. Well, that's very difficult, I think, for the average person to grasp in terms of why should a 1.5 degree change in global average temperature be a problem? My backyard thermometer goes by 30 degrees in a given day, from like 60 degrees to 90 or even a larger. So how can I get excited about a 1.5 degree increase? We need to talk instead about what are the consequences of that increase. But also, what we're dealing with is not simply, a climate crisis born of greenhouse gases that are making global average temperatures rise. We have an environmental crisis that is, about the acidification of our oceans and the warming of the oceans, the, plastic waste problem we have in our oceans and everywhere else. I mean, we're becoming overwhelmed by the byproducts of our existence and our metabolism, if you will. And we don't know how to deal with that, and we're not grappling with that. So we have a situation here that goes well beyond climate. It goes to what I would say environment, overall, all aspects of our environment. And, we should be talking in ways that I think allow people to more viscerally appreciate, the consequences of these elements. Because I think then, people can say, we really should do something. I don't know if we should do something about a 1.5 degree change in global average temperature, but we should really do something if, Miami is going to be 2 feet underwater in a few years.
A lot more than that.
So somehow making the connection in a way that people can associate with and then feel, compelled to act upon, I think is really important. Simon Sharp, he makes an excellent point in his book, 5 Times Faster, that nations are inappropriately focusing on the wrong things. They're focusing on an agreement about not achieving certain levels of global average temperature increase. They're not agreeing or even talking about how to do that. They're not talking about how do we decarbonize our atmosphere? How do we, take carbon out of the atmosphere, sequester carbon, and so forth. I'll definitely listen in next week when you talk to the fellow doing decarbonization. But, we should be talking about the strategies and methodologies and coming to agreements on things we should stop doing, things we should slow down doing, and mitigations that we should take or actions we should take against this. But instead, we're having conversations that are not even generating consensus around, we should prevent a global average temperature increase of this amount.
Well, it's worse than that. I mean, in the United States, they're actually shutting down renewable energy projects that are almost completed and pushing fossil fuels, projects that are much more expensive. You wouldn't even do them economically, but because your buddies paid you off, you're doing it.
Yeah.
So it's a pretty tricky. So let's turn it around and see maybe how can we use SETI to help address the problem. And one question I have for you: could framing climate change as a cosmic survival test be a more powerful motivator for action than what we're currently talking about today?
Yeah, I mean, possibly. I mean, if we could get this concept of the L variable out there, that people understand, that what we're dealing with here is an existential threat to our existence. And, it could mean that we never get a chance to find out if we are alone because we're not around long enough to find out if we're alone. But I think the other thing is that we tend to observe and understand environments at planetary scale. When we look at exoplanets or planets in our own solar system, we're looking at them at planetary scale. We're very interested in developing what we call a mission to planet Earth, which would be to put a spacecraft out at a Lagrange point like L2, where we could observe the entire planet at once with various instruments and look at both the technosignatures and biosignatures of Earth, and do that over time as well. So you have time series data. And the point of that would be, from our perspective, primarily to teach us, well, what does a planet with both technology and biology look like? What kinds of emissions does it have? And what kind of instruments or technologies might we need to understand what's going on that planet better? But at the same time, such an observatory would tell us what's going on Earth over time and give us, I think, helpful information about that, again, might help people understand what's going on with respect to our climate and the future of humanity, the longevity of humanity. So certainly thinking about things like the L variable, thinking about things at planetary scale. Also at planetary scale, there's no borders, there's no politics, there's no governments, right? All of that disappears. So you can purely and empirically look at something, a phenomenon happening that has no political elements to it whatsoever. It's just observable, measurable phenomena that are independent of, things like nation states. So I think that, and this is one of the reasons why with NASA and Georgetown University and others, we've been sponsoring these workshops on climate change through the lens of astronomy, astrophysics, and SETI. The whole idea being, can we bring a different perspective to this conversation that makes it less politically charged or even economically charged and is more purely, observational and consequential? What's going on? What do we see? What are the consequences, and what should we do about it?
And from a SETI perspective, what would a civilization need to do to stabilize its planet for long-term survival? Like, are any principles there? I mean, I think you spoke about a few of them already, but maybe you can sum it up. Or
Sure. Well, I mean, this is the subject of sustainability, and of course, on our planet, there are a lot of people who study sustainability, but usually in small, it's regional sustain. What's the sustainability of a city? What's the sustainability of a forest? What's the sustainability of an ocean ecosystem, et cetera. But I think, again, stepping back, what is a habitable environment? What does that look like? What are its characteristics? And how does one sustain such an environment? Now, the reality is that, Earth's environment has changed over, eons for reasons that have had nothing to do with species on the planet. Although, the first big environmental issue on the planet was the oxygenation of our atmosphere by cyanobacteria about 3.5, pick your number, billion years ago. So this was the great first environmental catastrophe for, anaerobic life. But it gave rise to the possibility for, mammalian life and ourselves to come into existence. So, we've had ice ages, we've had other, there's been snowball Earth has been theorized. We've had catastrophes associated with asteroid impacts, massive volcanoes, and so forth. So there are things that have changed and shaped the environment of our planet, and that will always be the case. And we talk about something else at the Institute, which is the coevolution of life and environment. So life and its environment co-evolve over time. They influence and impact and change one another. So it's a dynamic that is always going to happen, and it's inevitable. But how to make an environment sustainable, I think, starts with understanding what a habitable environment is, what those characteristics are, and what aspects of that element do you want, or of that habitability do you want to ensure never see a runaway phenomena? Like if your atmosphere has a certain composition of gases, you might want to look at modeling where you say, let's take certain gaseous compounds and run the model of what happens when they, go up in number or go down in number, and see. And based on that modeling, you might get an understanding. Well, we need an atmosphere that has sort of a balanced combination of the following primary molecules, and we ought to do things to sustain that, to maintain that balance, and or to correct it when we see it going out of balance. This is one of the amazing things about the James Webb Space Telescope, is that in addition to looking back to the origins of our universe, it also has a spectrometer on board, and one of its mission designs is to look at the atmospheres of exoplanets. And for your guests who don't know what those are, exoplanets are simply planets around other stars, and it's now becoming a common word. But 10 years ago, it probably very few people had heard about it. But anyway, James Webb can look at the atmosphere of planets orbiting other stars and tell us what their composition is. And we've already had a couple of interesting examples where people have been excited because of the compounds found in atmospheres that might suggest the presence of life on that planet. So in any case, I think there are ways for us to understand what constitutes a habitable environment, what constitutes an environment that is encouraging for the development and evolution and sustaining of life, and then do our best to maintain those characteristics. Like, you probably don't want an ocean to warm up too much. You probably don't want to have the pH of an ocean change too much. You probably don't want greenhouse gases to start running away in your atmosphere too much. And look at Venus, you know, that planet that's a habitable zone planet, but it had a runaway atmosphere of greenhouse gases, and the surface temperature there is well over 600 degrees.
Right.
You know, you could certainly cook pizzas there really easily, but you couldn't live there.
We did a show on that last week, by the way, because it was based on what Jim Hansen was talking about. And but of course, all these things you say, we actually know these things. We've increased CO2 content of our atmosphere by 50% so far, and we've actually done a doubling of greenhouse gases in terms of forcing already. And now we're learning from Hansen and others that that's actually worse than we thought, that it's really like a 4.5 degree climate sensitivity for a doubling rather than the 3 we thought it was, which is still certainly bad enough. Like, you don't have to go there.
Yes.
And so I think this is like, it sort of makes you question what the word intelligence means when you're talking about the search for extra intelligence here. You know, it's like, so it will be highly destructive if you pursue it, yet you pursue it with abandon. You know, you don't even like slow down. Yeah. I mean, you tried to speed it up. And that's just weird. I mean, by the way, you're working on climate change for a long time. You just get into this thing where you really just scratch your head sometimes and say, how could this be? How could we know what we know, and yet we continue to move forward as if none of this is true? So, okay. I think it's unless you have something else you want to add, time to bring Stacy in, get her question, and see if we have questions from others. And then we'll also have Eli come in too in a moment. But Stacy, welcome.
Hi. Thanks for being here, Bill. And yeah, you're sitting here. Question. I got so many. I don't know. It's tough to figure out where to begin. And we've had a lot of good chatter as well on YouTube. So maybe we can come back to that also. Oh no, speaking of, here it is. Okay. So Bill, you were saying about we have to reassure capitalists, etc. It seems like this whole thing it's the economy, stupid. Because I will often use the example of what would the aliens think if they were looking down on us, and they saw this is what we do as a society, sort of breaking it down into. I thought my thing is transportation. So the idea that we would have these unintelligent beings piloting their own little metal boxes and owning them and clogging city streets and, you know, wreaking havoc and killing people at such a high rate. And most of them are polluting the atmosphere and, you know, causing the end of all life on Earth. Most people would think that's kind of, or I would think intelligent life out there would think that was kind of dumb. Same thing would be about worrying about lines that are written on maps that don't even exist, that we would care about that more than, as you mentioned, functioning as a whole organism rather than these disparate parts. And then lastly, that we care more about the economy, this abstract thing of money that we made than preserving life as we know it. Anyway, do you think that aliens would think about this, or have we just are we just doomed, or what? Because it seems
well, I mean, it's a great question. You know, one of the things, for example, if an alien civilization were observing Earth in the same manner that the James Webb Telescope can observe exoplanets, and they were doing so over time, they would observe the CO2 and methane and other greenhouse gas constituents in our atmosphere going up over time, and they would see it going up at a rate that natural phenomena like, the long-term changes in Earth's orbit around the sun and things of this sort would not explain. And so they might be alarmed. They might, as I was alluding to earlier in the conversation, though, also see that this reminds them of something that they went through, earlier in their evolution, and they might either be hoping that we can figure out how to solve the problems that they themselves addressed and solved. I would love to think that they say, "Gosh, I wonder if we can help these poor souls out." But how they might do that, is a question. But and
Probably the same thing that AI would do.
yeah, I mean,
Because any form of intelligence would figure out we're the problem.
yeah, right. I think that they would look and say that this is of course the behavior. Much of the behavior is kind of insane and it's self-destructive, but it's not it's not self-destructive in a personal, like, suicidal manner. Like, we are taking our metal boxes, we're not intentionally driving them into concrete walls and killing ourselves, but we're effectively doing that indirectly by just driving them in the first place. And yes, there are vehicles which don't have emissions, but the extraction of lithium and other precious metals from the ground is not without its consequences either. So it's still, everything we're doing that involves personal transportation is problematic in that sense. And I always laugh at the Teslas with their bumper stickers of zero emissions. It's like, yeah, not quite. You're not burning a fossil fuel at the moment. That's true, but the energy that was required to get your lithium ion battery produces it almost is a wash. But in any case, I think aliens would probably look and either say, we're stupid, or we are doing things that they recall doing, and they overcame their stupidity. But I think it is very much about the time factor, and we live in the moment. We find it difficult to think past next week, and long-term issues and problems are hard for us to think that we should do something about that now. It's like when you're in your 20s, you don't think about your retirement, right? Except real smart people maybe do, but most of us don't. And so things on longer time scales and longer horizons that don't affect us today and the here and now, we sort of ignore, but we do so at our peril.
Oh, so that something you said about the Teslas. So does everyone at SETI ride a bike to work?
No, we don't.
That's the most intelligent form of transportation.
Oh, absolutely. I mean, we have a lot of people who live close enough by, and I'll tell you why I wouldn't do it. I live about 15, 20 miles away. I wouldn't do it because it would be very dangerous to do because of all the cars on the roads. So we're back to the car problem. If everybody was riding bikes, it would be a great way to get around. We certainly have a lot of people, including myself, who drive zero emission vehicles, but again, that's not like that's the answer, at least with today's technology. And we do our best for those who can, to use public transportation, which of course in our country is not very well advanced and not very capable.
Because we put the money into highways instead.
Yeah. So but for example, our board of directors has said, are you going to go back to a 5-day work week? And we have, in this post-COVID environment, and we've stuck with a 3-day work week. I mean, people are encouraged to go in every day if they want to. I go in every day. I kind of feel the need to, but I said I was tempted to go back to a 5-day work week, but then I thought, I can't, on one side of my mouth, talk about things like climate change and sustainability of a species, and on the other side of my mouth, force everybody to get into their cars 5 days a week and drive to work. So we're not going to make that change, and not because I wouldn't love to have everybody around us and have everybody in person 5 days a week. That's much more fun and engaging and exciting, but we're not going to force that to happen under current circumstances.
Oh, we should talk, Bill.
Okay. Anyway, speaking of talking, let's bring Eli in, and Stacy, you could go check out
Yep, I'll be back.
the comments there.
Mhm.
And okay, let's see. Let me get Eli in for. Oh, I'm sorry, you should be over there. Eli,
Hey,
welcome.
Thanks. So I'd like your thoughts on something that's maybe pessimistic for the endeavor of SETI, but I think very optimistic for the prospects of civilization based on non-detection so far. And that is, in the game theory of advanced civilizations, it's much better to observe than to be observed. My solution to the Fermi paradox can be revealed if anybody wants to search for the Monty Python video, How Not to Be Seen.
Right. Yeah.
So thoughts on the prospect that perhaps advanced civilizations figure out how to be efficient, communicate with each other without leaking signals, utilize resources efficiently to the extent that they don't need to expand endlessly, and go about their happy, safe, and secure lives without running into trouble.
Sure. Well, I mean, this is definitely an issue. One could say as well that even the Earth, in terms of its electromagnetic emissions, is more quiet now than we used to be, because so much of what we do to transmit information is over optical fibers, which don't leak anything into space. But I would say that it would be difficult to be entirely invisible. As an advanced civilization. You could certainly do so in terms of, the manipulation of the electromagnetic spectrum through things like radio and radar and so forth. You could probably find ways and workarounds. I mean, extraordinarily intelligent creatures would probably communicate with one another telepathically. They wouldn't need, cell phones and things of this sort. But, for example, on Earth, most of the radiation, well, virtually all the radiation we emit into space is what we would call leakage. We're not intentionally focusing any high energy, beacons of any kind at any wavelength, into space intentionally. But we have this envelope of electromagnetic radiation that is probably about 100 light years from Earth now, which would reveal our presence if advanced species had sensitive enough instruments. Our instruments, by the way, and the ones we use for SETI, are not sensitive enough to detect an Earth-like planet at more than, say, 20 light years out. So there is an underlying premise with SETI that some civilizations might be sending a beacon either to us or to somebody else, and we might be in the path, because you need a certain high amount of energy for a signal to be detected across the galaxy. However, the Arecibo Observatory, for example, before it collapsed, had the most powerful transmitter on Earth that was used for pinging asteroids, so that we could characterize asteroids and evaluate their potential threat for impact. And if you had an Arecibo-like transmitter and receiver on Earth, and you had another one at the opposite end of the galaxy, they would see one another. So, I think it is very true to say that sufficiently advanced civilizations might find a way to be less visible if that was of concern to them. That could be a conscious effort, or it could be just the way their technology evolves. But that definitely does play into things like the Fermi paradox and the L variable. The L variable was very intentionally, by Frank, said, how long does a technological civilization remain detectable? Not how long do they last? They may not be detectable because they evolve into a civilization that uses technologies or phenomena in such a way that we can't observe them or detect them. But don't forget that things like, weird compounds in exoplanet atmospheres would be more or less impossible to hide. So there's lots of different ways to look for life or the signs of life than, the direct observation of say, technological phenomena.
Now, you said it's quiet. We're quieter than we were, but I used to design communication satellites a long time ago, and now there are hundreds of times more of them. I mean, there's literally many thousands of active communication satellites surrounding the Earth. And yeah, it's supposed to be pointing down towards the Earth. But
They're pointing
actually,
mostly
all those antennas, by the way, that are pointing up towards the satellite, only a tiny fraction of that energy is hitting the satellite. You know, almost all of it's going out into space. So we must, just from satellite communications alone, becoming quite a bright object.
Yeah, I don't think that's very high energy, and you know, the kind of
Well, not high energy, but
we're not pinging satellites very often. You know, I mean, they're mostly autonomous in terms of what they do. We might have to ping them to change telemetry or give them instructions.
No, I'm talking about communication satellites. I'm talking about actually broadcasting signals to that satellite, like even a TV, you know, the normal TV relay satellite at geosynchronous orbit. You know, that antenna that is sending energy to that satellite, only a millionth of the energy actually gets caught by the satellite, and
Sure,
you know, 99.9 goes out into space.
yeah. Yeah,
So,
well, I
but
didn't say we've gone dark, but you know, depending on how you look at it, because we don't use, for example, broadcast television and radio the way we used to, which
Yeah.
were pretty high energy.
that's true.
Probably the most powerful signals we emit without, you know, for our own purposes are airport radar. Those are pretty powerful pings compared to, say, you know, satellite communications technologies. But
So you're saying though that only that the SETI, if SETI was looking at the Earth, it would have to be within 20 light years to pick it up.
with the kind of radio telescopes we have today, yes, that's true. We're building more sensitive instruments and more sensitive capabilities that might, you know, move that envelope out another 10 or 20 light years, but that's not very far.
It can't be more than 100, by the way, right? Because it can't be more than 100 light years, because we wouldn't be transmitting at that point, because we've only been transmitting for 100 years. So 100 light years is the farthest distance that is theoretically detectable of Earth, not
of Earth. Yeah, not the other way. We can detect
the other way, but not the other way.
Very far away, but yes, of Earth, that's correct. At least in terms of looking at our you know, electromagnetic manipulations.
Okay.
Yeah.
Very good. So thanks, Eli. And I'm going to bring Stacy in to see if there's any comments from YouTube chat that we should
Yes,
answering.
there's one at well, there are many, but the one I wanted to start with is, where does SETI get its funding?
Oh, that's a good question. So much of our funding comes from NASA and the National Science Foundation. We also do some research in you know, biotechnology that is funded by the NIH. We get some funding from U.S. Geological Survey, USGS, but mostly it's NASA. But about 30% of our funding is private funding. So this comes from, you know, we're a nonprofit, so it comes from philanthropy, people who are interested in supporting the work we do. And interestingly, the specific research we do around SETI using radio telescopes or optical telescopes to look for technological phenomena is privately funded. The federal government doesn't provide any funding for pure SETI research. So the kind of work we do that's funded by NASA is more on planetary science and astrobiology, astrophysics, et cetera. So so it's a wide range of funding, but and you know, so like any other nonprofit, we're always interested in people who are interested in our mission and want to get involved and want to help.
So one obvious follow-up is your funding being threatened at all by changes by the Trump administration?
Absolutely. I mean, you know, we're facing an environment in which NASA's budget has been cut in the administration's budget by like 28%, but the science budget within NASA is being cut by like 58%.
So they're targeting climate. I mean, they're targeting
well, and you know, one of the divisions at NASA and what is called its Science Mission Directorate has different divisions, and those divisions include astrophysics, heliophysics, planetary science, earth science, and biological and physical sciences. And the earth science one, of course, is not a priority in the current administration. So different parts of NASA's science will get, you know, hammered more than others. I am at least somewhat encouraged by the fact that the Senate does not want to see NASA's budget cut at all, and the House, maybe a little cut, but nothing like what the administration would like to see. So there's a hopeful scenario in which the House and the Senate negotiate, come to some compromise, and the reality is that NASA's budget doesn't get cut by very much when we start the new fiscal year. But we won't know for a little while, and in the meantime, NASA has been acting on the administration's budget, and they've already cut about 25% of the workforce. And for the most part, these have been the people who've been there the longest and have the most experience and knowledge. So NASA's already taken a huge hit in terms of its intellectual horsepower, if you will. And so there's a lot of concern in the community about how this is going to impact us. I mean, we're also worried about the science, data sets from missions, a lot of them, focused on Earth, and climate information, even weather data, which you'd think everybody would feel is important, all being threatened by these cuts. So, and it's funny because, okay, in theory, who wouldn't want America to be great? But one of the things that I've always thought was, well, if we thought about those aspects of America that were great at any given time, and we've always had problems, but NASA's always been one of them. One of the things that we all thought was great about the United States was NASA. It's been one of the most influential and respected brands of our country worldwide since its inception. And so, this is something that we associate with America's greatness, and yet, the administration wants to cut it in half. So yes, we are being threatened. We don't know the extent to which that happens, and we do intend to do the science anyway, to find other ways to find it. The science has to continue, even if the funding model has to change.
Well, hearing about all of the different agencies that you've received funding and knowing how they've been impacted, and I don't know how much flexibility you'll have to give your comments, but I was wondering on your opinion of trying to move civilization to Mars and funding Space Force / moving it to Alabama, while also having NASA's budget slashed.
Yeah, well, I mean, this is all politics, and I mean, the reality is politics plays a role in science. I would love to see, to live in a world where science was science and it had no political agenda. But of course, I mean, the administration has been very anti-NASA Goddard Space Flight Center in Maryland and the NASA Ames Research Center in California, because these are blue states, and let's go kill the blue states, and let's move things into red states. I'd like NASA science to be done in all states, but and make it fair. But yes, it's highly politicized, and this is not the way we should make decisions. As far as Moon and Mars is concerned, I mean, there's some inevitability of putting people on Mars and the Moon. It's a lot more difficult than the administration or anybody imagines. I mean, we do not yet know how to deal with the regolith on Mars, meaning the surface material, which is such a fine powder. We do not have the technology right now on how to filter it. So we couldn't create an environment that could even deal with air filtration, something as basic as that. We don't know how to do that.
Wow.
So it's not trivial to put humans on Mars for an extended period, or the Moon. And then we have the physiological issues of the sustained exposure to microgravity and also radiation associated with low gravity environments like the space station or the Moon, less so Mars, but still an issue. And then radiation exposure is a problem. So, there are a lot of challenges associated with that. But to make human exploration and human presence on these environments the singular priority of an institution like NASA, I think is short-sighted, and it misses so much more of what NASA is all about and has been all about. Most of the launches that NASA's ever had have not had people on board. They've been science missions, and all the farthest flung bits of technology from Earth, like Voyager, don't have any biology on board, at least not on purpose. They don't have people on board. They're machines, and they're scientific instruments. So I think that all well and good to try and address the engineering problems and achieve hopefully the more scientifically oriented objectives associated with putting people on Moon or Mars. I'm really not a fan of Space Force, so I guess I won't delve further into that topic. I'm militarizing space is A, inevitable, and B, horrible. So, but I think that it's all well and good to try and do those endeavors, because the challenges will result in new technologies being developed. Hard problems require a lot of innovative thinking. But and this is the other thing that I think is so short-sighted about the administration's perspective, is that by and large, federal spending on basic research, whether it's at NASA or NSF or NIH or any place else, it's not spending, it's an investment. It's well documented that these
Sure.
expenditures have a return on investment that is anywhere from 100 to 1,000% or more in some cases, and consistently. So if we could get people to start thinking about the funding that goes into basic research as investment, not spending, that it always returns a positive ROI, that maybe people would say, wait, we shouldn't do that. Every tech company on this planet, or certainly in the United States, owes at some level its existence and its economic strength to the fact that the government spent, traditionally lots of money on basic research, basic technology, science, engineering, and so on. Silicon Valley was not built by venture capitalists. It was built on the shoulders of robust federal spending on basic research back in the 60s and 70s. So we're having the wrong kinds of communication and understanding about the federal budget and about spending versus investment. And science and basic research are fundamentally, they're the foundation on which the House of Technology and Economic Leadership that this country has enjoyed for the last 75 years has been built.
Yeah, so it's very clear that that's what gave us our technological edge and dominance in the market, and it's
For sure.
purposely being destroyed. I should add that might be good for climate change.
Yeah.
Not the best way to do it, but it's certainly a way to just purposely destroy an economy in order to reduce emissions. Okay, I mean, there's better ways, but that's one of the
If that were the motivation, maybe that would be no.
I don't think it's their motivation at all. It doesn't
No.
matter what their motivation is. It's just what the results are. So that'll be interesting to see. Bill, this has been a fascinating discussion. And I think, at first people might say, well, talk about SETI and climate change. What is that? What's going on? But I think it really provides a useful perspective on what's happening here. We delve into the details and we look at aerosol emissions from ships and how that changes temperature. We do that here as well. And we also deal with the psychological side. We have communicators on about how can we get people to pay attention. But actually stepping back and looking at the Earth as, is it habitable? Is there intelligent life? What's the L factor for the Earth? Really helps, I think, put climate in perspective as this really incredible thing that we're not thinking about the way we should. And I think this is a very interesting way to do it.
I think the key point is that this is a planetary scale phenomena, right? It's not happening over there or someplace else. It's happening over the entire planet. We're not really facing that reality or dealing with it or thinking about it or talking about it in that context. So indeed, I think that, this is one of the interesting and usually fun or sometimes troubling aspects of SETI and astronomy and astrophysics is we tend to look at things from a big scale and from a distance. Mm-hmm. And we think about time and distance in very different ways than most people do. But that offers sometimes some interesting insights.
Yeah.
I have one last thing, twin sort of question comments here that has SETI considered putting out an SOS signal to say, please come help us? And then the other is there any chance that we would appear like ants and just not worth going to investigate or whatever, like we find ourselves so self-important and that we have dominated this planet and evolved and look how fancy we are, and that we just are nothing in contrast to actual intelligent life.
Well, I think aliens would say, anybody that's got Louis Vuitton has made it. So, that's the most important thing. But I would say that first of all, I don't think that an advanced species would think of us as ants any more than we think of chimpanzees or even dogs and cats as ants, and even ants are pretty impressive to us for those who study them. And this notion of of swarm, if you will, or networked intelligence and cooperative behavior. I mean, ants are rather extraordinary. So I think that we would a sufficiently advanced civilization is going to recognize that there's an advanced civilization on this planet that might be very immature compared to them, but probably not in the same way that they might look at creatures that they otherwise step on from time to time. But to your first question, the idea of sending a beacon, this now has a name, and it's called METI, and it stands for Messaging SETI. Not a great acronym, but in any case, but this is a highly controversial undertaking because there are, in the scientific community, to be fair, is pretty much divided, like half in like, this is a good idea, or no, it's not a good idea, because it's not a good idea because we're afraid of what who we might alert to our presence and what they might do about that knowledge. I think that's kind of silly. I mean, here we are with things like James Webb and our own radio telescopes and so forth. We're able to identify other technological species or living planets from a great distance. So my feeling is a sufficiently advanced civilization would probably already know we're here, whether we beacon them or not. But nevertheless, it's controversial enough that it's not done, and we don't do it. Our efforts are entirely passive. We're listening only, or we're observing only with optical instruments. We don't transmit. And even Stephen Hawking, the famed British physicist, felt that this was a dangerous idea. I don't agree, but and I explained that a little bit in the context of any civilization that solved its problems, the kind we're dealing with. And has come out the other side. It's hard to imagine them being malevolent in some way, but nevertheless, it's not done, and therefore we wouldn't do it, even though we might be motivated to say, "Please help." That wouldn't be a bad idea, but because of the controversy, it raises the question: well, who gets to speak on behalf of planet Earth, and who gets to speak on behalf of humanity here, and send a message? And what would that message say, and how would it be constructed? These are great thought experiments, by the way, and I think at the Institute we like to be seen as the place where these conversations have, to be thought leaders, to explore and discuss these kinds of issues, but we're not going to unilaterally send beacons out.
Well, we've kind of already done it. That's why I wanted to grab this in my office here. This is the Voyager plaque that went out to the stars to try to, if it was ever found by aliens, to try to describe where we are and who we are and stuff like that. That's a whole other discussion sometimes.
Yeah, well, in fact,
a little bit.
The
you got to
starburst,
find that particular spacecraft to make it work.
The starburst on that plaque is a pulsar map.
Yeah,
and, right. That was designed by Frank Drake of Drake equation fame, and Frank being also the first president of the SETI Institute, and Frank and Carl Sagan designed that. And, so there's a lot of associated history, but yes, we've sent information out. I mean, it's the likelihood of that plaque being observed by a technological civilization may be low, but it's not zero.
It happened in Star Trek.
That's right.
They did find it. Vidger, whatever it was.
Vidger. Yeah, that's right.
Bill, it's been a fascinating discussion, and I think surprising. I think for a lot of people who were, used to our regular climate discussions, but I think it really does help put the climate problem in perspective, in a more cosmic perspective, actually, and really makes us think about intelligence and things like that.
Sure.
What does that even mean?
Or the lack thereof, yeah.
The lack thereof, yeah. So thank you so much for being on. It was really great to have you here, and good luck with the challenges that lie ahead, in terms of funding and all of that kind of thing. But
Well, thank
but
you.
it's just such fascinating. I mean, that's what you're doing is like when anyone hears about it, they just they say, oh, that's so cool, right? You know, you're doing the kind of research that gets everyone excited when they hear about it. So that hopefully makes your job a little bit easier.
Well, the cool factor is pretty high, I have to say. I have a joke about the institute and my role at the institute, because we're here, in Silicon Valley. So I claim at once to have the coolest and the least lucrative CEO position in all of Silicon Valley.
Maybe
And
there's
that's
a little
probably,
trade-off on that. I don't know,
defensively true.
unfortunately.
But I'll take the cool.
But thank you
Over
so much for
widgets.
being here, and also to everyone out there. Please, we never mentioned this, but like and subscribe, please, and hit that notification bell. Leave a comment. Tell your friends about the program and that kind of thing to help spread the word.
Share.
This is important information, and we'll see you next week. As I mentioned, Brett Henkel from the co-founder of Svante. We'll talk about carbon capture. And thanks everyone for being here, and we will see you next time.
All right.
Bye-bye.
Thanks, Dan. Thanks, Stacy. Thanks,
Thanks.
everybody.